Hello, everybody. Hello, everybody. I can see my captioning is on working, so my microphone is working. Okay, let's pick up our discussion where we left last time. We were discussing the I/O devices and clock. Last week we assigned your homework number 3, which is about process scheduling again. At the end of the lecture, I can go over the maybe tomorrow morning. Tomorrow morning I will go over the homework. By tomorrow morning, please read the homework carefully. Try to understand it. If you have any questions, I will try to answer them tomorrow morning. Okay. Okay. So let's continue talking about this clock stuff. As we said before, clock is considered as an input-output device. You don't do much output, and in fact it is not a typical input device either, but it is typically there is a circuitry that tracks the time, and it causes interrupts at certain intervals. These intervals are either 50 times a second or 60 times a second, or sometimes different. Okay, so since these devices are causing interrupts, we consider them as I/O devices. Since they are I/O devices and they have their circuitry controllers, they need to have their drivers. So we need to talk about them in this chapter, input and output. So last time we said that the clock hardware is very simple. Well, at least it is much simpler than the other input-output devices, such as the hard disks. Still, we need to look at it. The idea is this: there is an oscillator, crystal oscillator. It produces a pulse at very precise interval. Okay, every time it produces a pulse, we have this counter connected to this oscillator. This counter is decremented by 1. Okay, so let's say this one produces a pulse 50 times a second. So this counter is decremented 50 times a second. When this counter when the counter becomes 0, it produces an interrupt, and that interrupt has to be handled by our operating system, of course. So if you handle this interrupt, that means that at every every time counter becomes 0, you are handling an interrupt, and you can do anything you like with this kind of interrupts. We call them timer interrupts. After this value becomes 0, you put this large value back to this counter again and start from the beginning. This crystal oscillator keeps running all the time while we have our computer on. Okay, so this is the basic structure of the clock hardware. We are not going to talk much about it. That's the only discussion. We will be mostly talking about how we use these interrupts to do useful work in our operating system. Okay, so last time we talked about this. We said that we use clock hardware to do these useful things in our operating system: maintaining the time of the day. The time of the day, the date is important because we put that information in our file metadata. Okay, we use it in a lot of places, and we use the clock information for process preemption, right? If a process runs longer than allowed, then it is preempted because of this interrupt. Otherwise, without this interrupt, otherwise that process would continue using indefinitely. Okay, and other things are like How do I know that which process used the CPU much? Accounting for CPU usage. We use clock data for that one. Also, in our systems, especially in Unix systems, there are system calls like sleep 3000, something like that. So I like to sleep for 3000 milliseconds. After 3000 milliseconds, wake me up. So who's going to keep track of this time? We do that using the clock information. Okay, so Ilhan, I think, started the class attendance. Class attendance is on now. Go there and sign it up. Okay, let me. Oh, no, don't do that. Just do this. Otherwise, our OBS would not. Okay, everything is working fine. Yeah. Okay. Okay, and as I said last time, we are going to look at this number 5. Is interesting, providing a watchdog timers, and we will define it. And maybe this one and this one is kind of similar. Profiling, monitoring, statistics gathering. We use the clock information. So clock is a very important input-output device, and we need to look at it in a more careful way. Okay, so maintaining time of the day is the first task that we are gonna do. So however we're gonna do that, when you boot up your computer, okay, you know the time either from the network or from someplace else. Okay, someplace else. So how do we keep the time of the day while the computer is running? Okay, so the idea is very simple. We know that I have an interrupt precisely 60 times a second. I know this, right? 60 times a second. If I count the number of interrupts that has happened, then I would know, okay, let's say January 1st, 1970 is my time 0. And from that day, I am counting the number of interrupts that I had seen. Okay, so if I like to know the current time of the day, what would I do? I just divide that counter by 60. That would give me the number of seconds passed since January 1st, 1970. Why did I choose January 1st, 1970? Because those are the days of Unix days, and they kind of made it standard. They started counting the number of seconds since 1970. But the thing is that this is so many ticks, okay? 60 times a second, 50 years. There's a lot of ticks, okay? So it looks like 32-bit counter will not be enough to count all of those years, because 32-bit counter would have, so 2 to the 32 over 60 is enough to count the number of seconds in 2 years. Okay, we should talk about tens of years. So 32 bit counter is not enough. Maybe we are gonna do it with maybe 64-bit counter. Okay, 64-bit counter. So this should be enough. 2 to the 32. Okay, if this is 2 years, okay, 2 to the 32, 2 years is a lot of years. Okay, so that should be more than enough. But we usually don't do it that way. Usually prefer, okay, A is if I keep 64 bits, That's going to be enough for 2 to the 33 years. Lots of years. Okay. But usually they don't do it that way. They like to divide it into two. I have a register that keeps 32 bits of data for the time of day in seconds. Okay, this is time of day in seconds, and then I have the number of ticks in current second. So this could be at most from 0 to 59. Okay, so very small register. I keep updating this one. Once this reaches the maximum number, then I can increment this one. Okay, or some people do it this way. Okay, this is counter text, counter in text. So this is 2 to 32 ticks, and this is the system boot time. So this should be good enough. If I keep my computer on for 2 years, this should be good enough. Okay, this should be good enough. Okay, so these are the 3 ways of keeping time of the day, and we do it with the help of the, of course, clock, and we use that time of day in many places in our system. Okay, any questions about the time of the day handling? Where is my, okay. I am trying to see if I have any questions. Maybe I should do it like that. No, all the questions are from the last one. Okay, then I will continue if there are no questions. So that was the first item. That was the first task. Okay, maintaining the time of the day. Let's look at preventing processes from running longer than allowed. This should be, we already looked at this many times. Okay, whenever the process is started, the scheduler initializes a counter to the value of that process quantum in clock ticks. Okay, so remember, preemption is used with the round-robin scheduling algorithms, right? Okay, whenever the process is started, the scheduler initializes a counter, the value of that process quantum in clock ticks. Every clock interrupt, okay, we decrement that counter by 1. When that value gets to 0, okay, the clock driver calls the scheduler to set up another process. Every time a clock interrupt happens, okay, it is the clock driver's task to handle it. Remember our I/O software? How was our layering of the I/O? It was our hardware, right? Then we have our interrupt handlers, and then we have our drivers, right? So that interrupt handlers and the drivers of the clock is responsible for making these decrements. Also, they are responsible for making these updates in our registers for the time of the day. Okay. So whenever I started a new process, okay, a process is running, I set up a counter that is equal to the number of clock ticks in quantum time, and every time an interrupt happens, I decrement that counter by 1. Okay, this is when the counter reaches 0, the clock driver sets up. Okay, the clock driver asks the scheduler to set up another process. This is how the preemption is done. This is how the preemption is done. In your homework, we don't do it that way. In your homework, we use our regular timers to simulate this process. Okay, any questions? Okay, good. Okay, another task of the clock is accounting for CPU usage. I should know okay, I should know how much time I have used for each process. All the serious modern operating systems do this. Okay, for example, in Windows, I have in my task manager, yeah, maybe I should, yes, okay. So it says that the Microsoft Edge used 1 hour of 2 hours of, is that hours? Yeah, 2 hours of CPU time. Okay, my draw board used 38 minutes of CPU time. So I need to keep these kind of statistics so that the operating system can report these to the user, but the operating system can make decisions based on this kind of stuff. Okay, this is especially important for the mobile computers. Why? Because you like to be careful about your processes that use too much CPU, because using too much CPU means using too much battery time, right? Energy. That's the most important, one of the most important things in a mobile computer. Okay, so these are the simple things again. To account for the CPU usage. Okay, this is different from, okay, preemption. In preemption, we like to prevent processes from longer than allowed. This one is for, I like to calculate how much time I use for this process. Okay, so whenever a process is started up, I start a second timer. This is not for preemption, this is for profiling. Okay, when that process is stopped, the timer can be read out to tell the CPU usage. So I keep that information. In the process table of that process. Okay. Another approach could be this. It is a little bit less accurate, but it still works. Okay. It maintains a pointer to the process table entry for the currently running process in a global variable. There is a global variable. Okay. Every time there is a clock tick, okay, I increment that global variable, but that global variable is specific for each process. So each process has its own global variable, and it counts the number of clock ticks, okay, for the when that process is active. Okay, so every time this is like that. Okay, let's say this is our process table. Inside our process table, I have my processes, right? This is process 1, process 2, and process 3. Remember, in our process table, we have our positions for the like the page table information, right? Maybe I have information about the registers, etc. And in one of the places, it is the clock ticks for the CPU usage. Let's call it CPU time. So each one has their own CPU time. Okay. If this process P2 is active, every time there is a clock tick, the CPU time is incremented. So why do we say that this is less accurate than the first approach? Why do we say that this simpler method is less accurate than the first method? By the way, how is my synchronization today? Let's do the synchronization check. 1, 2, 3, 4, 5, 6, 7, 8. How is the synchronization? Very good for Fatih.
Very good.
Okay, so it looks like it was my home network connection is bad. Okay, good. So you understood my question then in that case. Why do we say that the simpler approach is less accurate than the first one? This is a good question. Yeah, this question requires you to know both the details of process scheduling, interrupts, and the clock. Okay, the first one says that, okay, there is a timer. Whenever that process stopped, okay, I start a timer. Let's say when my process started, I know the time of the day, okay? I know the time of the day. When that process switches, I know the stopping time, so I can take the difference and I can put it in my process table. That's good. The second one is less accurate. It says that, okay, it keeps incrementing a global variable for each process at every clock tick. And it says that this is a little bit less accurate. Okay, any ideas? Well, I mean, when I say less accurate, it is not way off. It is a little bit less accurate. It takes time to maintain the pointer. Maybe you could say that, but the other one, you mean there is an overhead, Yusuf. Yusuf says that it takes time to maintain the pointer. Yeah, he says that there is an overhead, but the other method has an overhead too. Other method has an overhead too. Kamil says that because access time is more than a tick. What do you mean access time? Memory access time? No. I mean each tick is 1/50th of a second. Okay, 1/50 of a second or 1/60 of a second. Memory access is 1/billion of a second. No. Okay, 1/50 times a second is very slow. Maybe I did not understand what you mean, Kamil. You say that each tick is a so long, so you're saying what I'm saying. You're saying that each tick is a so long time. Okay, yeah, so I understood you wrong. Each tick takes so long, okay? Since I am measuring the things in terms of ticks, then I might be making error as much as 1/50th of a second. Yeah, that's kind of the idea. Okay, that's good. So you were right. I didn't understand your answer. Okay, good. So this is how you do the accounting for CPU usage. So this is our third. We did the second one. Okay, this was the second one. And accounting for the CPU usage. Let's look at this one then. Let's look at the handling of alarm system call from user processes. That is, however, we're gonna do this sleep thing. Okay, whenever I say sleep 3000, okay, I should get an interrupt after 3000 milliseconds. How am I gonna do that? Okay, well, I mean, these are not very difficult stuff, but they're important stuff. That's why we like to know that. And let's look at that one. Okay, handling alarm call from the user processes. As I said before, a process can request that the OS give a warning after a certain time of interval. Okay, this is very useful. For example, I sent some data through the network. Let's say I sent 1 kilobytes of data through the network, and I know that in 3 seconds I should get back an acknowledgement from the other side in the network in 3 seconds. So I need to wait for 3 seconds and check if I get the acknowledgement. What are you gonna do? Either you're gonna be in a busy wait list, busy wait loop. Okay, that will be bad for the CPU efficiency. Also, with the busy wait loop, you would not know how much time has passed. Okay, that's not a good thing. The second one is you will say that, okay, I'm sleeping for 3 seconds. Okay, this is used very frequently. Okay, so this is how they do it most of the time. They do it this way. They say that, okay, there could be more than one alarm pending. Okay, there could be more than one alarm pending. This is what we are gonna do. Okay, this is my current time. Current time in terms of clock ticks. This is 4200. And this is, by the way, this is inside the clock driver. Okay, this is inside the clock driver. And inside this clock driver, I said that my next alarm will happen in 3 clock ticks. Okay, in 3 clock ticks. Let's say these are the alarm times. One user said that wake me up at this time. The other one says that wake me up this time, wake me up at this time, wake me up at this time, and wake me up at this time. So if this is my current time, my next signal will be in 3 clock ticks, and my clock header keeps a linked list of alarms. In 3 clock ticks, I will issue an interrupt, and after that, in 4, 3 plus 4 is 7, okay, I will issue another one. 3 plus 4 plus 6 is 13, okay, then plus 2 is 15, then plus 1 is 16. So I am keeping this linked list of alarm times, okay, and every time there is an interrupt happens, timer interrupt happens, I decrement by 1, I decrement it, and I decrement it. When this one reaches 0, that means that this one will cause an interrupt. Okay, so I cause an interrupt. Then after that, what would I do? I would take this one and put it in here for now. Now I start decrementing it one by one. Okay, so that means that as many as timer requests can be handled in this way. No problems. As many as timers can be handled that way. So all I am doing is I am keeping the special value of next signal, and I am decrementing it by 1 at every clock interrupt. Okay, so this is how the interrupts handled in most of the systems. As I said before, these are not very difficult. These are not very difficult. Oh, maybe I shouldn't do that. These are not very difficult. Let me make sure my OBS is working. Yeah, it works good. These are not very difficult systems. Very simple but very important. Of course, since they work 60 times a second, they need to be implemented in a very, very efficient way. And there should not be any bugs, because any simple bug in that one will crash your whole system. Okay, any questions? Okay, now we are done with this. Now we are done with this handling alarm system call from the user processes. Göktuğ has a question. In a real-time operating system, RTOS, there is an operating system called RTOS, real-time operating system. Is the wake-up times are guaranteed after some processes calls sleep? A critical job can arrive and we cannot wake up the suspended process. It is although its sleep time completed. Göktuğ, the real-time operating systems are designed in a very special way. Their schedulers are not preemptive. You don't do preemptive scheduling in real-time operating systems. Because in real-time operating systems, you will say this. Okay, this is my CPU. In a given second, I have 1, 2, 3, 4, 5, 6 time slots. T0, T1, T2, T3, T4, and T5. I can have at most 5 processes running on this CPU. Process 1 will use this slot. Process 2 will use this slot. Process 3 is this. And process 4 will be this. And I will keep these two empty, just in case. And each process is supposed to finish its job in the given time slot. You cannot run longer than this time slot on a real-time operating system. Okay? So every time, in every second, each process is run. If that process has nothing to do, okay, if that process has nothing to do, the process says that I am sleeping. And the next second, again, I'm giving you this opportunity. Next one, I'm giving you this opportunity. Okay? So these kind of stuff don't happen. That means that real-time operating systems, they use their CPU very, very inefficiently. Most of the time, their CPUs are, even at the most busy cases of the real-time operating systems, your CPUs may be 60% loaded. More than 60% load is very dangerous for the real-time operating systems. Okay. So Göktuğ says, so they have their special system called such as sleep. Well, usually, there is no sleep. You just count the number of times you wake up, and that's it. Okay. As I said before, real-time operating systems are very, very restricted. They don't have secondary storage, for example. They don't have their desk. You cannot say that keep this information on the desk because disks need mechanical stuff, and mechanical stuff is not good. Yusuf has a question. Operating systems where process electricity yields themselves, does hardware require timer in this case? When you say yield, usually the yielding happens with the threads. Okay. When you say I am yielding, you are putting yourself on the ready queue. I am not running, but I am ready. Okay. When the scheduler decides that it is time for you to run again, you get your opportunity. There is no guarantee that you are going to run in certain amount of time. Okay. You are not guaranteed to run in certain amount of time. By the way, when you say I am going to sleep 300 milliseconds, 3000 milliseconds, the exact time is not guaranteed. Okay, it might be a little bit more than 3000 milliseconds, and we are going to see it in a few minutes. Okay, I don't know, Yusuf, if I answered your question right. When you do the yielding, no, you don't need the. Remember, yielding, we looked at the yielding when we looked at the threads, and the initial thread implementations, as you remember, is done in the user space, right? Is done in the user space. That means that in the user space, there is no preemption. Okay? A thread runs until it doesn't need the CPU anymore, and it says that I am yielding because there is no preemption in the user space. Okay? So theoretically, for your question, no, you don't need, you don't require any timers in that case. Okay, let's look at this watchdogs. Okay. This is especially important with the real-time systems. Okay. Let me try to explain it this way. Okay. Let's say when I start my operating system, somebody's saying me something here. What? Okay, there is nothing in there. Okay. Let's say in your operating system, okay, this is your OS, this is your scheduler, the basic stuff. Your OS. Your OS is in a continuous loop, okay. It schedules, okay. It does other OS procedures, and it goes into loop again, like that. Okay, this is your OS. Let's say I did this. In my loop, in my continuous loop, there is a operation that decrements a counter. Okay, that decrements a counter. That counter is starting from some high number. After a while, okay, this counter is going to reach 0, right? This counter is going to reach the value of 0, okay? Using this idea by itself is not a good idea, but let's say there is a special process, an OS process. This is called the Watchdog process. This process, okay, checks the counter. If it is 0, then counter is, let's say, 100 again. And this process keeps doing this in a loop. Okay. So why did I do that? I did that because if the operating system is running, it is scheduling, it is doing OS procedures and decrementing the counter, I expect that from time to time this counter is going to reach 0, right? If it doesn't reach 0 from time to time, that means that the OS is not running. Okay, something has happened to the OS. So what would I do? I would do this, else restart OS. Okay, so if that counter is not reaching 0 for a while, I know that I need to start my operating system. This is called a Watchdog Timer for parts of the system. Okay, maybe I don't do this for the operating system. Maybe let's say even not for the operating system. Maybe this is for windowing. Okay, my user interface, my graphical interface. If the graphical interface is not working, if it is not decrementing the counter, so the Windows or Linux, they start the graphical interface automatically again. Okay, so again, I use this to provide the Watchdog timer, and timer happens. This one runs. The Watchdog timer runs every time there is a interrupt. Okay, every time there is an interrupt. Okay, let's see what the book said about this. Okay. This is important, especially in the embedded devices. Embedded devices usually they never crash. In fact, they crash a lot, but they are restarted. You don't realize that it has crashed. Okay, because there is a Watchdog timer. That Watchdog timer, okay, it resets the system. So that if there is a crash, it knows that this crash has happened. Expiration of the timer provides that the system has run for a long time and leads to corrective action such as full system reset. Okay, Again, it is for embedded devices. This is very useful. Also, our modern operating system, they use this idea a lot. Okay. So this was another task for the timers, and finally we use the clock software to do profiling, monitoring, and statistics gathering. What is profiling? I am sure you have used profilers before. What does the profiler do? Profiler says that, okay, if this is your program, let's say this is your C program, these are your lines. The profiler says that this part of the code takes 20% of your time. This part takes 5%. This part took 0%. This was never run. So this kind of information is very, very useful, right? So I like to know what part of my code does the main job. So maybe if this 20% is the most of the time I am spending my CPU resource, then maybe I should be more careful about this part. Make it more efficient. Because most of the time my CPU is spending time in there. This is useful. So how does the profilers work? They get help from the operating system, and they get help from the clock drivers. Okay, clock software. At every tick, the driver checks to see if the current process being profiled. Okay, if so, it computes the bin number. That means that at every clock tick, if the current process is profiled, it saves the program counter information. It says that, okay, program counter was here and program counter was there. Using that information, later you build your profiling information. I am not sure if I can find a very sample program. Okay, maybe in the images I can see it better. Yeah, I think this one, automated data is it data profiling? No. Yeah, this one is better. This is, I think, Visual Studio. Is it Visual Studio? So it gives you the line numbers. Okay. So under this compute procedure, 58% of the time is for this vector 1 of something, vector then vector 50, vector something. So it knows which procedures, which functions are using the CPU time most. So to calculate this is not that easy, because you cannot do this statically. You have to do it dynamically while the CPU is working. Okay, and you have to do this in release mode, not in debugging mode, but in the release mode, so that you would understand better how the software is behaving in the real world. And you need the profiling information, profiling help from the hardware. And this is available with many operating systems and the development environments. Kamil has a question. So we use the statistics to improve scheduling performance. No, you don't use this. This has nothing to do with the scheduling. I have a single C program, okay? And in my single C program, I like to know which part of my C program is using the CPU most. Okay, that's what I like to know. So since this is a single CPU program, this has nothing to do with the operating systems. But to get this profiling information, I need the help from the clock hardware, okay, clock drivers, and from the operating system. There is a special program called Profiler, okay. This profiler runs your C program, but while it is doing this, it tells the operating system that I am profiling this process. When you are profiling that process, okay, at every clock tick, the driver check to see if that program is being profiled. If it is profiled, it just saves the program counter information. Okay, that program counter information would give you approximately where that process is spending its time. Okay, and then later you can map your information to the lines of code. Okay, profilers and debuggers are kind of come together. When you use a debugger, there is an option to use the profiler too. So if you have never used it, how many people used it? Anybody used the profilers before? You should definitely test your released program using a profiler to see if there are any pieces of code that gets never run, just dead code, right? 0% CPU time. That's not good. Also, you need to see which part of the program you should be more careful of in terms of efficiency. Okay, nobody used the profilers before? Both Unix and Windows, Visual Studio. Okay. Well, databases, they may have their own profilers, but they are in a different world. I mean, usually the database performance, they don't care much about the CPU performance. Their idea is using the hard drives more efficient and etc. Okay, so this was the final task of clock software. Okay, so we said that clocks are very useful. They have very simple hardware. Their software is written carefully. Although they are simple, they are very, very useful. But the problem is this. The problem is this. Okay. Clocks and interrupts, they have to be together. Okay. Without the interrupts, clocks has no meaning. Okay. Whenever there is a timer tick, okay, whenever there is a time related information, a time interrupt happens, okay, and I handle it. But the problem is this: with the modern CPUs, okay, interrupts have very large amount of overhead. Why? Because I need to set up my translation look ahead buffer. I need to set up my page tables, and I have pipelining, right? I have the pipelined architecture. I need to set up my pipeline again. The caches are invalidated and etc. Okay, so every time there is a clock interrupt, I take lots of hit. Okay, so to handle these, it's not a good idea to have this kind of interrupts. Okay, so they found this solution. They said that let's use the soft timers. What do I mean by soft timer? Soft timer is this: doesn't matter if you are gonna use the profiler or watchdog timers or the user timers, okay, or the other stuff, okay. Clock interrupts will happen anyway. So the idea is this: at every clock tick, okay, okay, whenever the kernel is running for some other reason, just before it returns to the user mode, Okay, it checks the real-time clock to see if the soft timer has expired. So the soft timers are handled not after the exclusive clock interrupts, but after some other interrupt. If there is an interrupt, for example, there is an interrupt happened. Why the interrupt happened? Because somebody needs to access the disk. Okay, the disk says that I am ready to do something. The keyboard says that I am giving you a keystroke. The network card says that okay, I loaded this one. Whenever there is an interrupt happened, okay, whenever the kernel is running, the kernel before returning to the user process checks to see if a timer has expired. If the timer has expired, then it handles it. So most of the time with the soft timers, you don't use the timer interrupts. Okay, this is because most of the time I need to go to the kernel many times. While I am handling it, I can check to see if the timer has expired. These are called soft timers. Why they are soft timers? Because with the soft timers, the wait time is not guaranteed to be exact. When you say sleep 3000 or 300, okay, when you say this, you're going to be waken up, but the wake up time may not be exactly 300 milliseconds. It could be a little bit longer, a little bit shorter maybe. Okay, because the kernel says that okay, I am running, I did something, and it looks like somebody needs to be wake up in a few milliseconds. I am going to wake him up now. Or it will say that okay, somebody had to be waken up like 10 milliseconds ago, so I will wake him up, wake that process up 10 milliseconds later. Okay, good. So these are the soft timers, and soft timers happen with system calls, TLB misses, page falls, IO interrupts, and the CPU going idle. So these will happen anyway. The operating system has to handle these. While it is handling these, after it is returning to the user process, it checks to see if there are any soft timers expired. So sometimes it is maybe 100 microseconds late, but it is better than eating 35% of your CPU to handle the timer interrupts. Okay, so this is the idea of soft timers. Any questions so far? Any questions? So it looks like it is time to take a break. Let's get together around 11:33. So it is break time. 10 minutes of break. Okay, class. Let's continue. So we talked about the clocks. We talked about the clock software, the interrupt handling of the clocks, and the clock software in the operating system. And then we talked about the soft timers to make the interrupt handling of the timers more efficient. So that was the whole discussion about the clocks. Let's look at very quickly other input-output devices such as the keyboard. Okay, like the other I/O devices, keyboard has a controller. Okay, you connect your keyboard to that controller, and you need to have a driver. Okay, so each time you press a key, an interrupt is generated. When you release the key, another interrupt is generated. That's what happens. Okay, so two interrupts per key press. One is for the press, one is for the release. Okay. At each of these keyboard interrupts, keyboard driver extract information about what happens from the I/O port. Okay, that's what it does. And everything else happens in software. I mean, so the keyboard is, if it's a straightforward keyboard, regular keyboard, it's a very simple device. It has an embedded microprocessors, and it communicates with the controller. So I'm not going to talk much about the keyboard. It's a simple input device. Since the keyboard has less than 128 keys, only 8 bits are enough to represent the key number. Okay. So every time there is a keyboard interrupt, okay, you get the key number. That key number is a 7-bit scan code, not the ASCII code. We don't deal with the ASCII codes in keyboards. Okay, ASCII codes are something to do with the upper layers of the input-output software, input-output I/O, input-output operating system software. Okay, at the keyboard level, at the driver level, we are only dealing with the key codes, scan codes. Yusuf has a question. When the key is pressed, some say it is software interrupt, the other say it is hardware interrupt. What? No, when the key is pressed, it is definitely for the operating system. See, okay, this is the hardware. These are your interrupt handlers. This is your keyboard software driver, right? Other I/O routines. On top of it, you have your application. Okay, you have your application. So most of the time, this part is your kernel. Okay, and this part will be in the user space. The dividing line might be different from system to system. Okay, so when you press a key on your keyboard, it definitely causes an interrupt. Okay, that interrupt is handled by the interrupt handler, and that interrupt handler, after it handles the interrupt, it gets the key code, and it puts that information in some kind of a buffer. Okay, if that buffer is full, it informs the driver, say that this buffer is full, or there is a new character, and etc. Okay, depending on the configuration. But how does the application know that there is a key press? If my application is running something like scanf, okay, scanf gets the result after the user hits the enter, right? So you wait until the user hits the enter, So who checks if the user had entered? Either it is the I/O software or the driver. Somewhere there. The application doesn't wait until application doesn't run a busy loop to wait for the enter key. Okay, it is a task of the I/O software of the operating system. Okay, that's the scanf. But for some interactive applications, remember those of you who took the object-oriented programming class, there was events, right? Events. We said that if there is a keyboard press, an event is created for that press. Okay, if there is a mouse movement, an event is created for that movement. Okay, you might consider those events as software interrupts if you like. Okay, but there is no such thing as like software interrupt. Software interrupt is system call. Okay, how do you make the operating system active? Through the interrupts. Either it is hardware interrupt coming from a hardware or a system call, system trap. System trap could be called a software interrupt, and that comes from the user side. But in terms of key presses and events, you might see this process like a creation of an event for a keyboard press. It could be viewed as a software interrupt, but it's definitely without the hardware interrupts. There is no input output there is no input from the keyboard for the modern operating systems. We cannot do polling or busy waiting to get a character from the keyboard. We have to use the hardware interrupts. Okay, good. So this is how the keyboard works, and there are many modes of the keyboards, like the raw mode or the cook mode. Cook mode waits until everything is handled and etc. I'm not going to talk much about those. Okay, so there are special characters, of course, with the keyboards, like a Control H, Control U. These are only meaningful for the driver, for the I/O software of the operating system. For handling the interrupts, Control H, Control U has no difference. It is no different than any other key press. Okay, good. Another popular I/O device is the input device, is the mouse. Okay. Nowadays, all of our mouse are like this, right? Do you see it? Let me. Okay, like that. So we don't use the mechanical balls anymore. There is a camera and the light source. The light source illuminates the tabletop, and the camera sees what kind of movements I am doing with my mouse. Can I turn it on? Maybe I would do with my other. Okay, here it is. This one is better. Okay. Do you see the red faint light in there? I don't think that you're gonna see it. Let me see if I can make it active. Oh, okay. I am just putting just right on top of it. I cannot see anything. Like that one. Yeah. Is there some kind of a reflection? Yeah. See that there's a light. So that light is illuminating my camera, and the camera on my mouse is getting that information and converting to a motion information. So every time there is a motion or there is a key press, my mouse is creating a interrupt. Okay, with that interrupt, okay, I produce those delta X, delta Y, and button information. Delta X means that I moved this much in the X direction. Delta Y is I moved this much in the Y direction. And buttons are the left button is pressed, right button is pressed, released, double clicked. Or sometimes I have this kind of new stuff, like not new stuff, but It is new for me, yeah, but this scroll bars and etc. So most mice, they report back at a maximum of 40 times a second. That's lots of interrupts actually. That's lots of interrupts. Okay. Good. So this is how the mouse works. What else? Maybe we can look at the screen a little bit more carefully. Screens could be as simple as dumb terminals. Dumb terminals means that I have 40 lines and 80 columns. Okay, 80 columns. What was the reason for 80 columns again? Do you remember those? I think at the beginning of the semester we talked about it. 80 columns is kind of standard. It is because you put 80 characters on a single punch card. Okay, it comes from the 1940s. Yes, yeah, that's punch cards. Punch cards. How old are punch cards? Do you know how old are punch cards? Punch cards are much older than computers. You know that, right? And at the end of 1890s, they had the punch cards. They used punch cards to put information. Okay, then later they read it and they don't. I wouldn't call it processed, but I mean instead of writing information to the paper, they write their information to the punch card so that it is readable. Anyway, so this is a dumb terminal. In dumb terminal, you have 40 times 80 characters. Okay, it's a special memory, and you put your character in one of those special memory locations using either memory mapped I/O or the I/O port space. And the task of the screen driver is to show that character on a CRT display or a printer. Okay, this is how the dumb terminal work. Okay, dumb terminal work. But we usually don't use dumb terminals. We use sophisticated graphic terminals. For the graphics terminals, okay, the kind of standard is using the X window system, derivation of the X window system. Okay, nearly all Unix systems base their user interface on the X window system. Okay, and the idea is this. Again, this is from MIT. Remember our Multics from MIT too. What was the main idea of Multics? Multics said that computing is a need. It's like electricity or gas or water. Okay, there is a central computing facility, and everybody is connected to that computing facility, and they have their clients running. Okay, the X Windows system says that this remote host is a large computer. Okay, you run your application on the remote host. It has lots of graphics related libraries. Okay, there is a layer of X client, and there is an X server on my remote desktop. Okay, so at my home, I run my Unix on top of hardware. On Unix, I have the X server. So this application program says that, draw a window like that, and draw an OK button, and draw a cancel button, and a writing area, a scroll bar there, etc. So all of these commands are sent over the network through the X protocol. My X server understands them and draws them on my screen. Okay, this was the idea, basically. But later we started running both the server and the client on the same computer. And nowadays that's what we are doing. So Windows computers and Macintosh, the Apple OS computer, OS 10 operating system, they use ideas like these. Okay. By the way, this is the line for the kernel space. So all the X-related stuff in Unix runs in the user space, but they are not part of the kernel. So the book defines these definition of these libraries. We don't use them much nowadays, but the X Windows system is important to know as the source of the many ideas of the windowing environments. Okay, this is a sample X window application. People used to use these kind of C programs to write graphical user interfaces. Okay, this is kind of a hello world application. So 2 pages of code, simple code. By the way, this is your event loop. Get your event and handle that event. Since this is not object oriented, there is no polymorphism happening, so you have to handle everything yourself. Get off all of your resources, get the event and handle it. Handle it. Okay, good. So I am not going to talk much about the GUI and the graphics much, and I think that will complete my discussion of the input and output, and I will start talking about the next chapter, which is deadlocks, if you don't have any questions. Do you have any questions? Any questions about input and output, this chapter? Chapter number 5. Okay, if there are no questions, then I will start a new chapter then. Remember that our first chapter was, chapter 1 was intro, and we talked about everything actually about that, about operating systems. And in chapter 2, we talked about the processes. That was the idea of abstraction of a CPU. And in chapter 3, we talked about the memory, abstraction of the memory. In chapter 4, we talked about the secondary storage, okay, file systems. And we talked about the input and output in chapter 5. We said that these 3 things, processes, memory, and file systems, are the 3 main things about the operating system. If you understand them, then that means that you understand the operating systems. Without understanding them, the I/O doesn't make much sense. Okay? Remember, when we talked about the clock, we kept talking about the processes. Okay? When we talked about the hard disks, we kept talking about the file systems and etc. Okay, so these are the things that are the most important. And then we said that I/O is important because most of the code of the operating system, they are done for the I/O. It is important. Now we are going to look at this chapter number 6. It is deadlocks. Okay, deadlocks. As I said before, the most important things about the operating system are processor, threads, virtual memory, file systems. I/O is important too. And the least important thing are the deadlocks. And I don't think that deadlocks should be part of any operating system course chapter. We should not talk about it. But it's kind of became a classical topic of operating system. Sometimes if you go to the interviews, they talk to you about deadlocks. Okay. Sometimes when you go to when you take an exam about operating system, they immediately talk about deadlocks, although they are not applicable, and we are gonna unfortunately have to talk about deadlocks. Okay. So this is the idea about the deadlocks. Let's say I have 2 users, Alice and Bob. Okay. They are using the same computer. Okay, mainframe computer maybe. Alice needs the scanner and printer. Bob needs the scanner and printer too. Okay. Alice has reserved the scanner. She needs to use the printer. Bob has taken the printer and he wants to use the scanner. Okay. Both of them has a single device. They need the other device. One of them is holding the other one. This is a typical deadlock. Okay. This is a typical deadlock. We show it like this. Alice and Bob. Okay. This is my printer as a resource. This is my scanner as a resource. Okay. Alice has taken the scanner. This is how I show it. Sorry. Alice has taken the scanner. She needs the printer. But Bob has taken the printer. He needs the scanner. Neither of them can continue. Okay, they are in a deadlock. So the definition of deadlock is this. The computer systems, operating systems, should be careful about these kind of cases so that while they are waiting, they should not wait indefinitely, because nobody is going to break this deadlock. They are going to wait until infinity, and nobody is going to handle this one. This is called a deadlock. Okay, and it can happen in any operating system that includes these kind of resources like the printers and scanners or tape drives and slots in systems, internal tables and memory, etc. Okay, this is called deadlock, and we are going to look at deadlock. And there are many ways to deal with deadlock. One of them is don't make any deadlocks. Just prevent this kind of situation to happening. The second one is detect the deadlock and solve it. Maybe the third one is the one that used by the Windows and the Unix and the most popular operating system. Don't do anything about deadlocks. Okay, we will talk about it. From the first days of the operating system, they are studied a lot. Okay, from 60s, 70s, they are studied a lot. The operating system theorists, not the practitioners, they love it because there are many theories to produce. There are many algorithms to design and analyze. But today is less of an issue of an operating system. Okay. Usually the database people, they deal with the deadlock. Okay. They deal with the deadlock. With the databases, let's say I have a database in this disk. I have this record R1 and I have this second record R2. Okay. And I have two processes, process A and process B. Process A, okay, process A has the R1 record, it needs R2, and process B has the R2 record and it needs R1. It's a typical deadlock in a database environment. This problem is a serious problem with the databases, and it needs to be dealt with the database management systems. But with the operating systems, usually we ignore them. Okay, so there is a deadlocks, and this is deadlock. Okay, and live lock. There is another version of deadlock is live lock. Okay, most operating systems, most modern operating systems, they just basically ignore the problem. Okay, they just basically ignore the problem because dealing with deadlock requires lots of CPU time, lots of code. So instead of making our operating system more complicated, why don't we ignore it? We are gonna be in a deadlock situation once a week, maybe once a month, maybe. Okay, at most, and we can take it, no problem. We can tolerate it. The alternative would be to prevent the deadlock. If I say that, okay, remember this, okay, just note this. If I don't have the second user B, there is no deadlock. The same thing again. If there is only one user, Alice, there is no Bob. Okay. If there is only one user, there is no deadlock, right? Alice can take both printer and the scanner, and she is done. Okay, this user A can get R1 and R2, and they're done. If I restrict the whole system to a single user, okay, one open file, one of everything, then I can solve the deadlock. But I don't want to do that because that would be too restrictive. Okay, it is like, don't use multi-programming because there is this problem of synchronization and the inter-process communication. Okay, or the race condition, right? We don't do that. We use it, but to prevent any deadlocks, maybe we just ignore it. Okay. So the problem is that the price is high, mostly in terms of putting inconvenient restrictions on the processes. Okay. So there is this trade-off between convenience and correctness, and should we be 100% correct, or should our operating system should be easy to use? And we prefer this one, easy to use. We don't have to be 100% correct all the time for the sake of practicality. Okay, so that's why I say that maybe deadlocks should not be studied in the operating system courses. Okay, so Yusuf has a question. But when deadlock happens in the operating system ends up in crashing. Yes, operating system crashes from time to time. My operating system, this Windows, is a very nice operating system, by the way. It crashes once every week or something like that, maybe once every month. I am okay with it. As long as it doesn't happen 3 times a day, once a month crash because of a deadlock is good enough. And frankly, I don't remember if I had a crash because of a deadlock. Well, usually you wouldn't know because the operating systems are complicated enough. They have enough reasons to crash other than the deadlocks. Okay, so if your operating system is crashing, it is not usually because of a deadlock. It is because of something, a driver problem, or a bug with the current updates and etc. Usually deadlocks don't become much problem. Of course, I mean, the correctness says that your operating system should never deadlock. Okay, if you are sending a rover to the Mars, okay, to Mars, and you should say that there should never be a operating system crash. But as you know, those computers are real-time operating systems, and they are very, very restricted. And the chance of getting a deadlock for those operating systems is very low. Okay, even if that happens, okay, they have very good watchdog mechanisms. They start their operating system again. Okay, and that happened in one of the Mars rovers. Actually, their operating system was crashing and it was restarting again and again and again. Even with those kind of very mission critical computers, crashes are expected. It can happen. And to prevent like a 1% chance of getting a deadlock in a single year, if I need to add like 20% more code to my system, no, I'm not going to do it. I will take it. I will take the risk of getting a deadlock and crashing the system. Okay, that's the modern idea. That's the modern solution. Because the cost is too much to prevent the deadlock, detect the deadlock. The cost is too much. Anyway, we are going to look at it. Okay, if somebody asks you about the deadlocks in operating system, tell them that you know about them. Tell them how to detect. You know how to detect them. Tell also them that nobody does the deadlock detection. Nobody does the deadlock prevention. Okay, so to look at the deadlocks, we need to define this concept of resources. Actually, we have been using resources a lot. A resource is anything that must be acquired, used, and released over the course of the time. Okay. For example, a disk drive. You acquire the disk drive, you read it, and you release it. You acquire the printer, you print your stuff, and you release it. You acquire the scanner, you scan it, and you release it, etc. Okay. The memory is the same thing like too, right? I mean, in your memory, for example, a mutex, a semaphore is a resource too. Okay, you get your mutex. Okay, you down your mutex. You get into your critical region. You use it, and you up it. You release it. Okay, mutexes are resources too. Okay, it could be physical devices, shareable things like main memory. Okay, and database records. These are all resources. If you have resources and if you have multiple users, then there is a chance of getting a deadlock. Okay. Preemption is something that you use to solve deadlocks. Okay. Remember the preemption? When did we use the preemption? We use the preemption for the CPU. If somebody is using the CPU for a long time, we say that you shouldn't be using the CPU for this time. We preempt it, right? You remember that? You preempt it. Okay, so we are going to use preemption not for the CPUs, for all resources. Okay, remember our Alice and Bob example. If Alice says that if Bob is using the scanner or if Bob is using the printer, just preempt it from Bob. Just take the printer away from Bob, and Alice can use both printer and the scanner at the same time. And when she is done, Bob can use both of them. That would be a solution. So if you can preempt a resource, then you would solve the deadlock problem. But the thing is that some of the devices are not preemptible. CPU is preemptible. Why? Because you will say that you stop. I am going to save all of your information. Okay, I am going to save all of your information. When you return back, you will continue using the CPU. You could preempt the CPU. You could preempt the memory too. How would you preempt the memory? You will say that, okay, I need this much. I am going to swap you out to the disk. Okay. Whenever it is your turn to run again, I will load your data back from the memory again. So this is how you preempt the memory. But how would you preempt the printer? How would you preempt the printer? While the user is printing something like 50 pages document, I printed the 10th page. Can I preempt that printer because the job is not done? Okay. If I preempt that job, after the 10th page, I will start printing my documents. If somebody else preempts my printing, again, all the pages will be mixed together, and that will not be a nice picture. So some of the resources cannot be preempted. Printer is not preemptible. Scanner is not preemptible. Okay. See, but there are nice ways of preempting the CPU and the main memory. Okay. So as I said before, preemption is a good way of solving a deadlock situation, but it is not always applicable for the resources. Okay, good. In general, deadlocks involve non-preemptible resources. Okay. To get a resource, and these are the order of steps: request the resource, use the resource, and release the resource. These three things. Okay. So let's look at a few examples actually. Let's say our resource is a semaphore. Okay. Okay, I have a semaphore resource 1. To use that resource, I down the semaphore, I use the resource and release it. Step number 1, step number 2, and step number 3, like this one. Request the resource, use the resource, release the resource. If the resource is not available, I will be blocked here, right? I will be blocked here. I will be waiting. This is a single resource example. If I have more than one resource, okay, with a single resource, you wouldn't have any deadlocks. But if you have more than one resource and more than one processes, there could be deadlocks. And with the two resources, okay, get the resource 1, get the resource 2, use both of them, okay, and release them. I have this example. This is a deadlock free code, and this is a potential deadlock code, okay. I have two processes, process A and process B, running in parallel, of course, okay. Process A and process B are using exactly the same code, okay. Get the resource 1, get the resource 2, use and release. Get 1, get 2, use and release. Okay, these are two things. These are two things. How about the second one, code with potential deadlock? Get resource 1, get resource 2. See this one? Let's say the order is reversed. Okay. I get this resource 1, and then at this point there is a switch. And this one says that I will get resource 2. So let me do it this way. Okay. First I get this resource and I switch to process B. I get this resource. So one of them has resource number 1, the second one has the resource number 2. And then another switch happened. I try to get the resource number 3, resource number 2 here, step number 3. It will not get the resource number 2 because it is already taken by process B. And this one will be blocked, and there will be a switch, and this one will try to get the process resource number 1. It won't get either. So this one is blocked here, then this one is blocked there. And there is no way these two processes will continue. It's a deadlock. So in terms of drawing these diagrams again, process A and process B, resource 1 and resource 2. The process 1 got the process A got the resource 1, and the process B got resource 2. Process A wants to use the sorry, this should be a square, okay. Process A wants to use the resource 2, and process B wants to use the resource 1. So there is a deadlock here. This is deadlock free. This doesn't mean that this part B is going to have a deadlock all the time. It could have. There is a potential deadlock. That's what makes the deadlocks bad, problematic, because it doesn't happen all the time. It's like the race condition. There is a potential. So this is another example of a deadlock. Okay, good. Any questions? Okay, this is the definition of standard definition of deadlock. A set of processes. Okay, this is processes. With a single process, there is no deadlock. Okay, if you don't have a multi-process operating system, okay, there is no deadlock. Or if you have a single resource, there is no deadlock. A set of processes is deadlocked if each process in the set waiting for an event. Okay, everybody is waiting for something, but that event can be caused only by another process in the set. Okay, I have 1, 2, 3, 4, 5 processes. They are waiting for something. All of them are waiting for something, but that thing can be caused only by the other processes in the same set. So nobody can continue because everybody is waiting for others. This in real life, outside of the computer world, This happens with the traffic. Okay, vehicle traffic. It's called gridlock. Gridlock. Okay. Gridlock example. Let me see if I can get any pictures. Okay, gridlock example. Yeah. This is a... Maybe this is a better picture, yeah. Yeah, Wikipedia is a nice... I didn't see this one. I don't remember this one. In traffic gridlock, okay, this is a... Okay. Make it bigger. See, nobody can continue in this case. Why? Because this guy cannot continue because of these red cars. Red cars cannot continue because of blue cars. Blue cars cannot continue these reds. As you see, it's called that gridlock. It's called a gridlock. Okay. Resources are the roads. Okay. Resources are the roads. And the processes are the cars. Okay. Let me show you that example of... Okay. So this is a gridlock again. The pedestrians are okay. I guess they continue, but all the rest are... Okay. Whenever the policeman comes in, the police comes in here and they give citations to these drivers here. Because in New York City, it is illegal to stop in an intersection. You cannot stop in an intersection. You don't get to say that the car in front of me stopped and I stopped. No, you can't say that. Okay, you can't say that. Okay, good. So this kind of things happens. This kind of things happens with the real life, and in computer world, we have examples of this kind of deadlocks with the resources. Okay. As I said before, people have studied deadlocks a lot. In 1970s, they say that for a deadlock to happen, 4 conditions has to be met. These 4 are important. People usually ask them in the interview. Just memorize them. Okay. These 4 things has to happen at the same time. If one of them is missing, there is no deadlock. The first one is mutual exclusion. Okay. Each resource is either available or assigned to exactly one process. You cannot share it. Okay. You cannot share it with the mutual exclusion. You cannot share it. Either the printer is used by a process or it is available. 2 processes cannot use the printer at the same time. Okay, it has to be that way. That's called mutual exclusion. Hold and wait. Okay, the processes, they hold the resource and they ask for more. Okay, then this has to be there. Okay, if you say that you cannot use more than one resource at the same time, then hold and wait cannot happen and resources cannot happen. If you restrict your processes to a resource only, you could use only a single resource at the same time, then you would prevent all the deadlocks, but that would be too restrictive. No preemption. Okay, resources cannot be taken away from a process involuntarily. You cannot take the printer away from a user. You cannot take the scanner away from the user. So no preemption. If the preemption is possible, then you could prevent the deadlocks. And of course, there should be a circular wait. Somebody is waiting for somebody else, and that somebody else is waiting for this process. Okay. If any of these conditions aren't present, all of them has to be there. Deadlocks can't occur. Okay. And these conditions are tied to the operating system policy. For a single process operating system, there is no deadlock. For a single resource operating system, there is no deadlock. But if you have many processes running and many resources are being shared, there is a chance of having a deadlock. Okay, so we are going to look at each of these later, maybe tomorrow. Okay, I talked about this. Okay, there is a way of modeling deadlock. First, let me just draw diagrams and see if we see a deadlock. Okay, this is a deadlock situation. These are the processes. C and D are the processes. T and U are the resources. Okay, A has a resource. A is holding this resource of R. B wants to have this resource, requesting a resource. This is holding a resource. This is requesting a resource. And if you have a loop in your allocation graphs, these are called allocation graphs, then you have a deadlock. Okay, let me show you this example. I have two resources, RST, three resources, RS and T, and I have three processes. If I run these processes one after the other, first run A, then B, then C, there is no deadlock. No parallelism, no deadlock. Okay? No parallelism, no deadlock. A wants to do this. A wants to get R and S and then release it. B wants to use S and T, then release them. C wants to use T and R, then release them. Okay? If I run A first, then B, then C, no problem. Or C, B, A, B, A, C, doesn't matter, in any order. With no parallelism, there would be no deadlock. Okay? There would be no deadlock. But if I run them in parallel, let's do this. A requests R. Okay? A requests R. A got it. B request S. B request S. B got it. C request T. Okay, C got it. So I executed the first lines of each process. Okay. Then A request S. I am done with this one. A request S. And then B request T. I am done with that one too. Okay. Now C requests R. C cannot get R because R is already used by A. So there is this loop. Okay. There is this loop in this direction, closed loop, and there is a deadlock. So this is called, these diagrams are called resource allocation graphs. And if you draw your resource allocation graphs, and if you see a loop, a closed loop, then you have a deadlock. Okay, this is one way of detecting a deadlock in a restricted environment. Why I'm saying restricted? Because I assume that there is only one resource from each of these resources. Kamil has a question. Kamil, oh, he took out his question. I think I am out of time, but Kamil, if you have your question, just ask, or maybe we can continue tomorrow morning. I couldn't understand why the first is can't. Kamil, could you just fix your question? I don't understand what it is. I think he has a solution and he says that why don't we do it that way? Well, I mean, this is a carefully designed example to make a deadlock. Well, I mean, this is kind of obvious, right? I mean, R A holds 1, B holds 1, C holds 1. A wants the second. Okay. A cannot take the second. B cannot take the second. And C cannot take the second. Nobody can take the second. So they will wait indefinitely. Each one, okay, there are 3 resources and 3 processes. Each one needs 2 resources. And if I am unlucky enough, each one will take a resource. The second one will not be taken because second one will be held by somebody else. I still don't understand your question. Kamil, just ask this question tomorrow morning, okay? We will continue tomorrow morning. Okay, that's enough for today. I will see you tomorrow morning. Just read your new homework. Tomorrow morning, I will start from your homework. Ask me questions about it, okay? Don't delay your questions until the end of the submission period. Okay? I'll see you tomorrow morning. Oh, I am running. No. Okay. Oh, that's bad.